Then, first of all, I will expand the plan of this course. For the first lecture, I will talk about ultrametric absolute value and the ultrametric analysis. And in the two first lecture, we will try to be familiar with such a setting. After that, we will talk about differential algebra. What I mean by that, the algebraic notion of algebraic nature of a differential equation. After that, we will enter to especially the case where we define a differential equation over an ultrametric field, and we will study the radii of convergence, and we'll observe the particularity of such a differential equation that we will call p-adic differential equation. If we will have time, we will explain the area of application of such a p-adic differential equation. Then, I start by some notation. We denote by the ring of integer Q, the field of rational number, and R, the field of real number. Then, first of all, we will define what is it an ultrametric absolute value. And first of all, we will what is an absolute value, and after that, we will define the specific case of an ultrametric one. We will study what is a sequence in such situation, what's the properties of a series over an ultrametric with where the geometric is where the absolute value is ultrametric. And in the end, we will talk about the completion with respect to an ultrametric absolute value. Then, first of all, ultrametric value and the induced topology. Then we fix the definition. We fix K a field. Then an absolute value on K is a map such that we have it's a map from K to the positive real numbers such that it satisfies the following properties. The first one is for all x in K, we have secondly, the absolute value of 1 is equal to 1, and for all x, y, and k, we have have this. Then the triangle. Triangular inequality. Now, as an example, we know the usual one. Usual one, the absolute value on R, real numbers and Q, and even complex numbers. We know that it has another type of that maybe we are not that usual, that is for any fields. We can define an absolute value over such a field. That we call this absolute value is called is defined as follows. X is equal to 1 if x is different from 0 and equal to 0 if x is equal to 0. And we call it the trivial absolute value. Then we observe a particularity about the trivial absolute value is the following. For example, if we have x plus y, then it is equal to the maximum of this 2, 1. Which is strictly for sure then if, for example, we replace this inequality with this equality, that such if then we still have an absolute value. Satisfy. One, two, three, then this one. And instead of the fourth one, and satisfy for all x and y, satisfy. then it is an absolute value. We call this inequality the strong triangular inequality. And in this situation, we say that the absolute value is ultrametric. And as an example, we say we already talked about the trivial absolute value. Now we will show other example. For example, then we fix a prime number and we define the value. Therefore, we define a map called evaluation on P, defined as follow. We'll explain what I mean by that. Union minus infinity. Then if it is 0, then we will associate minus infinity, plus infinity. And for any elements m, then the valuation of m is the maximum of E such that P power E divide m. Then we can extend this up as follow. To Q. And if we have m over n, then it is VP m minus VP n. And this application satisfies the following. Then we have the valuation of 1. It is 0 because P never divide 1. We have the value if we have a product of two numbers, then VP m plus VPN, and we have VP m plus n is greater or equal to VP to the minimum of 1. And by this application, we can define an ultrametric absolute value over Q as following. Then we fix a number less than 1, a real number less than 1, and we define the absolute value on Q as follows. The element X is then R VP X. And we obtain all the n in this situation. And I denoted this. Prefer to denote it. It was 4. Then and this app is called the p-adic. Absolute value. Then now we will talk about the metric. Then if we have an absolute value, then like as in the real case or in as in the real field, as in the field of real numbers, then we can associate to this absolute value a matrix as follow. Just metric. Okay, and use it. Right, absolute. Okay, so first just to define the metric as follow. And for any xy, then the distance between x and y with respect to this is x minus y. And with respect to this metric, the addition and multiplication on K are continuous. And we will call a field endowed with a field endowed with an absolute value, ultrametric absolute value, and ultrametric field. And the topology here is an ultrametric field means that we have an absolute value on K, and on K we consider the topology and used by this metric. Just to be careful, the situation, if we are in the ultrametric setting, we have many properties that are not available in such setting. For example, just I will say the first particularity about this this metric. First one is, for example, if the lemma, if we have x and y in K, xy. Okay, and can we fix just k ultrametric field and x, y, and z. Okay, then we have, because of the strong triangular inequality, then the distance between x and y is equal to or is equal to this distance. We denote by notation of for an element A, K, and R. Just for fix arithmetic field. And an element K and R is a real positive number. Then closed disk is like in the matrix. Oh. And open this. However, be careful. Now we will see the difference between the metric spaces that we are used to. We have the habit to use them. And what is the difference between, for example, if you are in a normal space, a normal vector space over R, then this situation cannot happen. Yeah. The closed ball is the closed and the open ball are open and closed in the same moment. Same time. And this is because the ultrametric strong triangular inequality. And because of that, we have the following lemma. then for A and B and K, then and R greater or equal to R2, then if two disks, open or closed disk, it doesn't matter, open or closed, this, but I just write it for the closed one. If the intersection of two disks are non-empty, then probably one of them will be in the other. And here, since we fixed that there is a ball which is bigger than the other, then probably we have this one include in this one. And is in the special case, if the two radius are equal, then we have the equality. More. And the same hold for open disks. This is mean that if you have a disk in the ultrametric setting, then any point of this disk can be the center of the disk. Just come back to the previous example. For example, when we talked before about the trivial valuation, then the trivial valuation induce the district topology on K. And now I will prove this. And the point that it is problematic about ultrametric spaces is the fact that since the open disks are open and closed in the same moment, then we got a problem concerning connectedness. And the only proposition, the only then every notion in the ultrametric setting need more work to define the thing in a good way. Donc let K Then as a topological spaces, K is totally disconnected. Which means that for all elements X in K, the connected component of K containing X is equal to the set singleton containing only X. And the proof. That X in K. Then suppose we will use the contradiction to prove this statement. Suppose that so X is different from X, which means that there exists another element in this component. There exists Y in then for some epsilon small probably have then P minus Y and epsilon intersect with C epsilon, and this is different from the empty set because in both of them there exists Y is in the set, and we choose epsilon to be such that this set is strictly included into the connected component. Then, since the connected components are closed, and this doesn't matter, then we will just focus in the topology on the inducer topology on the connected component, and this one is connected. On the other hand, we know that in K, this one is open and closed in the same time. Which means that which means that all this one, this is in K, open and closed in Cx. And since this set is different from Cx and different from the empty set, it contradicts the fact that Cx is connected. And then we finish the proof. Now we just will give some notation about that we will use later, but not this time. But I prefer to do to give it now. Notation. Then there is two notation, different notation. Someone called me this one or this one. They are the same and they are defined as follow. It is the closed open disk centered at 0 and with the radius equal to 1. And okay, yes, the open disk. This is the particularity. We will see why it about ultrametric setting. Now proposition. Then, okay, is a occurring. Also bring of K and MK is the maximal ideal of and K is the fraction fields of okay. What do we mean? What do we mean by local sobering? It means that there exists a unique maximal ideal, which means that if all the non-invertible elements are in the same ideal and they are, which means if, for example, if A is not invertible, don't, if it is not here, then A is invertible. Then, having that, and if we set then K is exactly, this is a field and it is called the residue field of K. And the interesting part about that is there exists a natural map from from OK to, which is the quotient, called reduction. And the idea is sometimes, we will see later, but for the moment, we need some extra properties on K to talk about that. For example, the idea later is if we have, for example, a polynomial with coefficient in this ring, then if for in some assumption if for example we have x in a bar, and we consider the reduction of p, which we just reduce the coefficient of p on K, then we got a polynomial here on such that is equal to 0 plus some other assumption. Then, and we will see this, then we can find x on OK such that p-adic is 0. But it's important. There is some other assumption I didn't, and we will see this is the called lemma answer. Maybe we will see the next lecture. This is just, it's not the purpose. We need other properties on K that we will see just now. Just to have some example about, then for example, if we have Q and use with the p-adic absolute value, then it's something particular here is then it will be something like that, m over n with and the absolute value, the valuation on n is equal to 0. Then m is in Z and n is in Z minus the ideal induced by P. And we know in and this ring is local, and the maximal ID so in this situation is just P and here the residue fields, but I will not use this is just a particular case. After we will before talking about the residue field, we will talk about the completion of the field, and after that talk about the residual field. But this is just a, and in this situation we have the FB isomorphic to Z over PC, the finite field. In this situation, we cannot always, for example, have a recovered solution in Q. We need another property which is the completion of Q. To talk about that, just I need other properties that are necessary to recognize ultrametric, the ultrametric absolute value. And field and absolute value. Then the following properties are equivalent. The first one then second one for all elements. And we know that for any fields we can embed Z in these fields. Then for any element n on Z, then the absolute value is strictly less than 1. Yeah, is less or equal to 1. In particular, if the field is finite, then the only absolute value that we can put in, can undo, is the trivial absolute value. And the last one is define the same topology. And that's why, for example, from 2, that's why we say we can, there is another name for ultrametric absolute value, which is a non-Archimedean absolute value, because of this second property. And because of this property, we cannot have the Archimedean property. Which means that if we have for all x, y, such that there exists, it's implied that there exists n in n such that this cannot happen, because the absolute value of the integers are strictly less than 1. And for this reason, ultrametric fields are also called non-Archimedean fields. how we talk about sequence and series. Then we fix a field. In all this section, we fix an ultrametric field. And let be a sequence. Okay. Then before talking talking about Cauchy sequence and such stuff, I prefer to give some special property that we will find only in ultrametric setting. For example, then the first one may be strange if we are not used to, if just start by defining what we mean by conversion sequence. We say, well, this is the same as in usual case. We say that xn converge to x. Since we use the metric space, then it doesn't matter. It's always the same for sequence and everything. But we have some special properties that we will denote just x and tan to x. It's just a notation. If and only if, and for all epsilon, positive epsilon, there exists n0 in n such that for all n greater or equal to n0, it's implied that xn minus x is strictly less than epsilon. Then the first thing to remark about that is if x converge to x, then there exists n0 in n such that for all we have exactly that. This means that the sequence of the absolute value of the sequence will be constant from a certain rank. Why? Because for example, for epsilon strictly less than x, then we can find such and there exists n0 such that strictly less than epsilon. This means if I want to compute xn, then it is equal to xn minus x plus x and in this situation, since is different from x because of that, then we have exactly this equal to the maximum of the two. This is not complicated to see, but I just point out this because just to be careful. For example, this means if we have, for example, yes, yeah, for sure. Yes, x is different from 0. Otherwise, it's yes. Otherwise, it will converge. It can the absolute value of the sequence can converge to 0. This means that if with such that the sequence, the real sequence, stationary, stationary means that for then we can, then the sequence cannot converge to x. In other words, that if we are too close to an element, then we have the same absolute value as this element. Then the other part is a series. Then the series converge if and only if the sequence, the following sequence, or for some easier or not necessarily, is a converge. And if you remember, then usually, if in the usual case, we have this sequence. Converge, then probably we should have that this sequence converged to 0. Otherwise, this one cannot converge. This one cannot converge. However, in the ultrametric case, this condition suffices. Then we have the equivalence. Which is which make think easy about convergence theory of the theory, is equivalent to the fact that this theory is converging. And you know here, for example, in the real case, we have the counterexample, the theory 1 over n, and n is not convergent, even if 1 over n is. Here for the field, the usual case of just, however, here it's always working. Now, we know how we talk about Cauchy sequences. The idea about Cauchy sequence, the fact that if I just define them. As in the usual case, then Xn is a Cauchy sequence. If and only if, for all epsilon positive, there exists n0 in n, such that for all m and n greater than n0, we have less than epsilon. This means it means it's just something like we have our space, we have our sequence, and we have and after there is a moment where all the terms are too close. However, it's not necessary that they will converge to something. And for example, for R, if we have a Cauchy sequence, then probably it will converge to an element. And in such situation, we say that the fields is complete. However, it can happen that we have the Cauchy sequences, but it cannot converge to anywhere. For example, if we have Q, for example, the field of rational numbers, and if we can always construct, for example, a sequence in Q, and it converges, for example, to P, and in such situation, such a sequence is a Cauchy sequence on Q, however, cannot converge on Q because P is not a rational number. It's like the fields, just the definition. And it is a general definition, but I will restrict our case to ultrametric fields. It's convergent. And a field who is not complete is a field who contains a gap in his topology, so something like that. Just as a simple example of a complete field, ultrametric fields, we just have because the topology is too fine. That's why we have such if is trivial, that's this because no. This is not ultrametric, but I will give it here too. Not even for the p-adic case is not complete. And even with the usual one, this we know. This means that we cannot approximate in such a field. That's why we need to construct a bigger fields which satisfy this property. And hopefully, for any field, there exists a unique field that extends the absolute value for which every Cauchy sequence is convergent. Then just to have good definition, we just need to define what are the morphism between two ultrametric fields. Definition to define the uniqueness of the completion of a field. Then, first place, it is a morphism of ring, and we know that morphism between two fields is necessarily injective. Then, moreover, it is a morphism of ring, and it is an isometric morphism of ring. Isometric. What I mean is that for all x and k, we have now this means that if you want to have this means, for example, remark, which is important, because it can happen that two absolute values are equivalent, but it will not define the same ultrametric field, because for example, this fields and these fields are not isomorph, even if they have the same topology, because the embedding is not isometric. The identity is not isometric. Now we will state our, but probably we will prove it later, the next lecture. Then this theorem that construction here, it is something about all metric spaces we can construct a completion, but for ultrametric field, we can handle the situation otherwise. Most algebraically, we can write many of stuff using algebraic construction. And with the ultrametric absolute value, the strong triangular inequality make things more easier than the other one. Even if it is not, we are not. It's not a natural way to look at a metric, but it makes things easier for the computation. Then, first of all, there exists a field that we really not like that, complete, such that there exists an embedding particular. This means that this is an isometry, which means that this absolute value extends this one, and the image where the image is dense in this field. Where we see where we Secondly, this field is unique up to isomorphism. And we say, since it is unique, we say that is the completion of K. For example, here for Q, this here I just stated, but the theorem is also available for general absolute value. And for example, the completion here of Q is R, because we know that Q is dense in R. And since it is unique, then probably R is the completion of Q. Then I will stop here for this lecture, and we will continue the next time. Probably the next time, the next session, it will be in Tuesday in the evening, and it will be online and offline. And I just do not notice the lecture at 8:30 will be online, only online, and the other one can be online and offline. Then, is there any questions? And if there is no question, we can then we see you the next time.
Arrête la vidéo avant de sortir le truc.